We're going to be talking about work and energy. Part of the problem with work and energy, Danielle, is the word work has a specific meaning in English. It's not what it means in physics. In physics, the word work has a specific meaning. In English, if I say I'm doing work, what most of you think is work means tiredness. It means getting sweaty. It means getting fatigued. And that is not the physics meaning of work at all. First of all, work in physics is a scalar. It can be negative. That just means you're losing energy. It can be positive. That means you're gaining energy. But it doesn't have a directional component to it. There's no work north. And it's defined as the product, which means the equation is going to have a times sign, of the force component in the direction of motion and the distance moved. Work is equal to force times distance, but the force and the distance have to be in the same direction. If they are not, no work is being done. And there's one more idea. This equation only works for a constant force. After Christmas, we're going to be looking at some rocket science. We're going to be looking at going into orbit. As you move further and further from Earth, what happens to the force of gravity? It changes. It's a changing force. We will not be able to use force times distance very often in outer space. We're going to have to develop a better, more complicated, but better equation for work. And in fact, I'm going to introduce it to you a bit later on today. What are the units? Well, I guess it would be a Newton meter, because force is newtons and distance is meters. But this unit is so important, we give it a special name. We call it a joule, symbol capital J. So example 1 asks, how much work does Ethan do when lifting a 50 kilogram mass up to a height of 5 meters? Do me a favor, if you would be so kind, underline the word lifting. Ethan, what's this question asking me to find?
Work.
So right now, I'm going to go, okay, work equals force times distance. Let's assume, Ethan, that you're lifting the object at a constant speed. If you're lifting it at a constant speed, what's the object's acceleration? And so the forces are, I'm looking for word that begins letter B. So this force right here would really be the force that you apply while lifting. But can you imagine the free body diagram? What are the forces acting on the object that you're lifting? Get the obvious one. And force lift. I think they're going to be the same. I think we can make the argument that if you're lifting at a constant speed, is going to be the same magnitude as mg. Grace, is that okay? I'm not going to walk through that argument again. From now on, anytime I see the word lifting, my next thought is going to be, oh, which force? mg. I'm not saying that gravity is the force. I'm saying it's the same magnitude, but it's just up because gravity is normally pointed down. But you lift things by applying a force up. And then because it's a vertical distance, we often use the letter h for height. You may have seen that one last year because we also said that's the equation for gravitational potential energy, mgh. So in this case, now 50 kilograms, it's about 130, 140 pounds. So a small-ish person, 5 meters, it's about a flight of stairs. So this would be how much work it would be to piggyback an adult up a flight of stairs, as long as the adult wasn't on the heavy side. It's going to be 50 times 9.8 times 5. What do you get? Going to be 2450? That's a guess. Okay. It was going to be a little less than 2500, and I figured it'd probably be 50 less because there's lots of 5s kicking around there. So 2450 joules. Probably all of you if it was like a matter of life and death, if you were carrying somebody away from an injury or danger, all of you could do this much work. All of you could probably, with adrenaline, piggyback someone up a flight of stairs. Now, if I said piggyback them up 30 flights of stairs, maybe not so much, but up one flight of stairs, you could probably all do this much work. And I'm just saying that so you get an idea that 2,500 joules, fair bit of energy, but not a lot of work. Not a lot. I forgot to change the name. This, instead of Connor, should also be Ethan. I changed the one name and forgot to change the other one. Suppose Ethan can't lift 50 kilograms straight up. What's that? Cross out the word suppose. Okay. Ethan is unable to lift 50 kilograms straight up. Okay. That's what they were saying. Instead, he decides to push the mass up a ramp at an angle of 30 degrees. If he ends up at the same height, how much work will he do? We're going to ignore friction and we're going to dolp. So here's the ramp. Ethan, what angle is the ramp?
30.
Yep. Okay. Here's the height. I'll call it h. And let's put the mass right here. Hey, I'll bet you this is a job for a free body diagram. What are the forces acting on this mass? Get the obvious one. And because there's a ramp, I'll break it into its components. mg perpendicular, mg parallel. There would be a normal force. And then I guess there would be a force up the ramp. This is Ethan pushing it up the ramp. Ben, what's this question asking me to find? How much what?
How much work?
Well, work is force times distance. Do me a favor, draw a little line over to the right. We're going to draw also another dolp right here in just a second. Now, the force and the distance have to be in the same direction. So, which force is Ethan applying? Well, I guess F applied. And don't write this next bit down. I think this is the distance, and the reason I don't want you to write this next bit down, it's really going to gum up the diagram, but that's in the same direction as the force. We said the force and the distance have to be in the same direction for work to occur. So I'm going to really quickly redraw this triangle a little smaller, where this is still 30 degrees, this is still H. I'm going to call this D. That D is at opposite, adjacent, or hypotenuse. Now, there's a bit of a problem because I've got an H there, which is not hypotenuse. So I'm going to write HYP for hypotenuse. And the height, H, I think is opposite. Which trig function? Sine 30 equals H over D. How would you get the D by itself? I think you would times the D to the top. At the same time, divide the trig function. I think D is equal to H divided by sine 30. Now, I'd like you to calculate that for this specific example for just a second. So if you go the height of 5, which is what the original height was, divided by sine 30, you get 10? Okay. I'm not going to put in a 10. I'm actually going to put in this algebraic expression over here, but I want to also look at the numbers. So F applied times D, F applied, which force must F applied be the same size as if Ethan is still going at a constant speed? Okay, so I can replace F applied with mg, two lines, is sine theta. and D is h over sine theta, what happens?
Sine cancels out.
You get exactly the same answer as before. Ethan does the same amount of work. Now, do me a favor. Can you, up here, can you crunch mg 50 times 9.8? Because this is what Ethan was unable to do. He couldn't lift it straight up. How many newtons of force would it take to lift it straight up? What is 50 times 9.8? 490. Can you go mg sine? How many newtons of force does it take to push it up the ramp? 245. Twice the distance, half the force. You're still stuck with the same amount of work, but for what it's worth, a ramp is an example of what we call a simple machine. In physics, what a machine does, it doesn't make jobs less work, but it lowers the force at the expense of increasing the distance. Oh, you want to cut the force by 3, by a factor of 3? You're going to have to move it 3 times further. Sorry. Okay? So it reduces the amount of force required, but the trade-off is that it increases the distance. The amount of work remains the same. Some of you may have seen this at Science World. At Science World, they have a lovely little swing set that you can sit in with a rope pulley, and in one of them, you lift yourself up, and there is no force multiplier. There's not a good simple machine. I think that one is maybe a 2-to-1 ratio. You're not doing quite mg, you're doing half of mg. And then there's another one where it's really easy to pull yourself up, but you're having to pull and 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 pull, because the trade-off is we've increased the distance, the amount of rope you have to move for you to raise yourself that. I mean, you, the one I'm talking about at Science World, you've seen the one there? Yes? Okay, it's a fun one. So, point being, a ramp doesn't decrease work. It does lower the force required, though. I'm going on a bit of a rant because somebody, one of my students, I think last week, was telling me, oh, the pyramids were built by aliens because human beings. No, they had ramps, and we found the ramps. We found the actual architecture. And in fact, it's a famous physics calculus problem. You can actually calculate how much work it would take to build the pyramids, how much work it would take to raise all the blocks. We can't do it with your math skills because it's a decreasing slope and a changing number of blocks, and that's one of the things that calculus was invented for. But you can find the amount of work it would take to build the Great Pyramid at Giza, which is the big one. And then if you divide that by about the average number of joules a working human being can put out, and then multiply it by how long it would take, you get about 20 years, which is pretty much bang on what the records show that it took. It was not impossible. You don't need aliens to invent things, please. Oh, in real life, of course, there'd be friction. You'll end up doing slightly more work because actually your applied force wouldn't exactly be half. It'd be a little bit more than half, but you're still coming out ahead if you just can't apply a big enough force to lift it straight up. So it's still less than lifting the object directly. I'm not going to ask you about simple machines, but I just wanted to show you as kind of a nerdish, to me that's kind of cool. You get the same answer both ways. Next page. Suppose we have a ball at the end of a rope being swung in a circle, kind of like I'm doing right now. I am applying a force through the rope to the ball. I'm feeling tension in my hand. How much work am I doing? How much work am I doing? Well, if we look at my little diagram here, tension is along the rope acting that way. But the direction, the distance I'm moving is in that direction. How much work am I doing? Why 0? Because the force and the distance are not in the same direction. Now, although work is a scalar, that doesn't mean it can't be negative. Usually what we say is if the force and the motion are in the same direction, we call that positive work. If the force and the motion are in opposite directions, we call that negative work. And the context here, Justin, is if you're in the same direction, this object is gaining energy. If your force and distance are in the opposite direction, this object is losing energy. So it's not saying somehow that a negative work is south. It's you're losing energy. It's a magnitude. So, although work can be a positive or a negative, it's not a vector. It has no direction. What if the work is at an angle? Did I say angle? It's components. I'm going to walk you through it, and I think there might be one like this in the homework maybe, but I won't be asking you a component question on the test. So here is the classic lawnmower question. Looks like a wagon to me. What I mean is we have an angle theta on flat ground. Okay? How would you calculate the work done by the child on the wagon? Well, work equals force times distance. I think on your formula sheet, I don't think I put a times symbol between them. I think I just wrote the F and the D touching, right? Probably would be what I would do. But the force and the distance have to be in the same direction. Oh, you know what? We should break this up into components, where this is Fy and this is Fx. Which force is in the same direction as the distance that the wagon is moving? So here, work is going to be Fx times distance. Well, hypotenuse adjacent, which trig function is Fx going to be? Of course it is. Work is going to be the force along the handle, the applied force. If you want to, you can write F applied times D times the cosine of the angle theta. That's actually the definition of work. The work done for a constant force, you can, if you want to, add this to your blue sheet, but not to your yellow sheet. Is that there? I'm going to get rid of the word applied, just FD cos theta. Now, what if theta, what if the force and distance are in the same direction? How many degrees would theta be? Can you, on your calculator right now, can you find the cosine of 0, please? Oh, and I get force times distance, which is the equation that I told you at the beginning. What if they're at right angles? Can you find the cosine of 90 degrees? Is it 0? And there's the piggybacking. I'm sorry, you're not doing any work on Nick if you're piggybacking. Okay. Do me one favor before you turn the page. You may even want to draw an arrow pointing to your force equation, this one right here, and you may on the blue sheet just make a little note, F must be constant. What if it's changing? Good question. Work is force times distance. You're going to get 3 definitions of work today. And the first one, my fallback, the first one I always go to is force times distance. But if the force is not constant, work is also the area underneath a force versus distance graph. How will you know when to use that one? They'll give you a graph. You laugh, that sounds Captain Obvious, but I'm telling you, don't overcomplicate it, okay? First thing you'll ask is force times distance. Now, notice, Ben, in this graph, we have a force versus distance. The force starts out at 1 newtons, but it finishes at 3 newtons. That is not a constant force. This situation, whatever is applying the force is pushing harder and harder and harder and harder and harder. So part A right here says how much work is done moving this object from 2 meters to 6 meters. What does this question want me to find? How much work? I can't go force times distance because I have a changing force. By the way, the most common mistake I see chemia people go, oh, the answer is going to be 3 times 6, and they go 18. Can't use force times distance because the force is changing. Also, we're going from 2 to 6. You know what? Let's do this. D, 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 D. You want to know how much work? Don't write this down. It's going to be that area right there. This shape has a name. It has 2 parallel sides and 2 sides that aren't parallel. Does anybody know what we call this shape?
Trapeze.
Close. It's the same root. It might even be the same root word. So now that he's given you a hint, you should all be embarrassed and come up with the English word that he was trying to get as a second language. What word? It's a trapezoid. Trapezoid. How many of you know the formula for the area of a trapezoid? They teach it in Europe. We don't teach it here. And this is one of the few times I think we're okay. The reason we don't teach it here is it's redundant. Every single trapezoid can be broken into a triangle and a rectangle. And those we do have equations for. Trapezoid is 1/2 bracket A plus B close bracket times H. By the way, if you want to see what the trapezoid formula is, see me sometime during a flex like I'm walking through. It is kind of nerdly cool. In fact, you'll learn that a triangle is a special case of a trapezoid. What? It's a limit as the base approaches zero. So, if I want to find out how much work, don't write this down. Why can't I just go force times distance? Because the force is not constant. So you can write down W equals area of shape 1 plus area of shape 2. I usually use Roman numerals to number the areas, and I use a capital A for area. What shape is area number 1? What's the area of a triangle? Believe it or not, that one I think I did put on your formula sheet. I think somewhere, probably on the back page, you'll find a picture of a triangle, and I think you might even see some of the trig ratios there as well. You might even see Pythagoras, but I'm pretty sure you see area, what is it? I usually write that as base times height over 2. What's the base? How long? 4. What's the height? Careful a little bit. It's going to be 4 times 1 over 2. Ethan, I'll bet you can do this in your head. Oh, you look a little pressure there. Yeah. Then, area 2 is a rectangle. What's the equation or formula for the area of a rectangle? That one I didn't give you on purpose. That one you kind of should know. Length times width. Some people say base times height. Same difference. I'll go length times width. What's the length? 4. What's the width? I think 2. Ethan, in your head? How much work did we do in total? Okay. So you can also find work by simply doing the area underneath a force versus distance graph. How will you know when to do that? I'll give you a graph. You've heard me slip a couple of times during this lesson. Instead of saying the word work, I've used the word energy. And the reason is energy is also measured in joules. Energy is the ability to do work. And since work is force times distance, I guess that really means, Aisha, that energy is the ability to exert a force over a distance. Can you exert a force over a distance? Then you can do work, then you possess energy. And there are many, 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 many forms of energy. Energy, Trevor, is one of the key concepts in physics. In fact, if you ask me, this next bit of the lesson we're going to be using in the next unit, and the unit after that, and the unit after that, and the unit after that. We're going to be using it. There's motion energy. The fancy word for motion energy is kinetic. Heat is a form of energy. Usually heat is created by friction. There's all sorts of types of potential energy. Potential energy is just stored energy. The type of potential energy that we're going to look at the most is gravitational potential energy. This is stored energy. Spell it right, Mr. Dueck. Possessed by a lifted object. When you lift an object, you temporarily store energy in it. Another type of stored potential energy is chemical energy, like in gunpowder or in the food that you eat. Even the terrible lunch that you eat, still there's stored energy in there somewhere. Sound is a type of energy. There's elastic energy. That's the energy stored when you stretch a rubber band or an elastic band. Nuclear energy, that's the E equals mc squared energy in the interior of an atom. There's all sorts of types of energy. The two main ones we're going to be looking at are, the three main ones we're going to be looking at are kinetic, heat, and gravitational potential. Example 5. Sometimes when you do work, when we apply a force over a distance, we make an object move. Fill in the proof to find an expression for motion energy. Well, work equals force times distance. I'll start with that. And then I'll say F equals what? So I can write this as MA times D. And then I'm going to get clever for a reason. You won't quite see why I'm doing it for a couple of lines. But what I'm going to do is I'm going to put a 1/2 in front of the M and a 1/2 in front of the M and the 2 in front of the AD. If I multiplied by 1/2 and I multiplied by 2, what have I really multiplied by? 1. So have I changed anything? Have I made it look different? Yes. Now, why did I do that? Right there. VF squared equals VI squared plus 2AD, which means that 2AD can be replaced with a VF squared minus a VI squared. The 1/2 M just drops down like a domino. And if we start at rest, if VI is 0, I get hoodie off, kiddo. Kinetic energy equals a 1/2 mv squared. That's the kinetic energy equation, 1/2 mv squared. It's a scalar. It does give you joules. So I guess another way to calculate joules would be kilogram meters squared per second squared, I guess. Joules. No vector symbols. Since kinetic energy is a scalar. In a jelly donut, by the way, there's about 10 to the 6th joules of energy that your body can consume. There's another unit of energy. It's very small. It's called 1 erg, and that's about the equivalent of a mosquito push-up, or about 10 to the negative 13 jelly donuts, or about 10 to the negative 7 joules. Do you have any golfers here? Yeah. A golfer wishes to improve his driving distance. What would have more effect? Doubling the mass of the golf club or doubling the speed of the club head? I heard someone say mass. I heard someone say speed. The good news is one of them's right. Why speed? The speed, the V, has a squared on it. So absolutely B. Doubling the speed gives 4 times as much energy And in theory, the ball would go 4 times further, although you'd lose some other stuff a little bit along the way. This right there, this example and that line explains most of modern sports equipment. In the last 30 or 40 years, unless the equipment has a standardized mass like a baseball bat, most equipment, especially in golf and in tennis, it's gotten lighter, not heavier. Now, it's a bit of a trade-off because there is an M in the equation as well, but does that M have a squared in it? No, so we'll make it a little lighter because you'll get way more bang for your buck by being able to swing it faster. Double the speed, 4 times the energy. Triple the speed, 9 times the energy. In theory, 9 times further. And that's why I'm because you've done golf lessons, when we're talking about driving in particular, it's all about your club head speed. That's what makes the biggest difference. Okay. Next page. Sometimes when we do work, we lift an object and give it height energy, stored energy due to its position, gravitational potential energy. We already derived it in the first line. We said it was mgh. We did it on the first page. We argued that if Ethan was the one lifting at a constant speed, the force that he was pushing up with was exactly equal to mg, and then we said let's call the distance h. This only works as long as you're close to the Earth. As you go further from space, G changes. From 9.8, it gets smaller and smaller and smaller. Oh, it's going to be positive 9.8. We're in Scalarville here, so we don't put a negative in for the 9.8. There's no direction. So we will have to derive a new cosmic potential energy after Christmas. But for now, we're going to stay near the Earth. Usually we focus on mechanical energy, which has 2 main types, kinetic and potential. This brings us to the best definition of work, but it's also the most complicated definition of work. So work is what times what? Force times distance. Now, on your blue sheet, not on your yellow sheet, but on your blue sheet, somewhere near where you have W equals force times distance, you might also want to mention that it's the area under a force versus distance graph. Now, you can write area under a F versus D graph, or if you want to, you could do a little dollp. You could say F, D, do this, and draw a little arrow. That's also whatever works better for you, but somehow on your blue sheet, make a little note. You can't put it on your yellow sheet, but make a little note that, hey, work is also the area underneath a force versus distance graph. Whatever works for you, whether you're a diagram person or a writing out person. Both of those are not the best definition of work. Here's the best definition of work. It's also the most cumbersome and pain to use. The net work on an object is equal to its total change in energy. In algebra, we say this: work is equal to the change in potential plus the change in kinetic. What's change in anything? Final minus initial. So really this is work equals PE final minus PE initial plus KE final minus KE initial, but I write it like that. I think I gave you that one on your formula sheet this time. I never used to. I used to make kids memorize this one, but I think I stuck it on there, yeah? Was I really that nice to you? Wow. This is called the Work-Energy Theorem. Some textbooks will simplify this. If you're on a flat road and your height's not changing, then your potential energy isn't changing, and so this whole thing cancels. So you may see some textbooks simplify the work-energy theorem into just the change in kinetic. I don't think that's correct. It's the change in kinetic plus the change in potential. It's only just the change in kinetic if you're on flat ground. Put your pencils down and look up. I love example 8. I love example 8. I love example 8. Example 8 is a beautiful question. Why would I say that? Okay. Well, Kimia, what's example 8 asking me to find?
Work.
Okay. Don't write this next bit down, but I'll show you how my brain works, no pun intended. What's this question asking me to find? First thing, don't write this down. My brain would mentally do this. Well, work is force times distance. Do you see a force in newtons or a distance in meters anywhere in this question? Do you see a force in newtons or a distance in meters? Don't overcomplicate it. Do you see any of those? My brain would scratch out that definition of work and move on to the next one. Work is also the area underneath a force versus distance graph. Did they give you a graph? My brain would scratch out that one, and I would move to my third definition of work, the Work-Energy Theorem. Can you read it to me, please, kiddo? It's on your formula sheet. Work-Energy Theorem, the third definition of work. You're missing something in front of it.
Potential energy.
You're missing something in front of that. What are the triangles? Hey, okay, ready? What does it say?
Changing potential energy. Plus changing kinetic.
And you could write change in kinetic plus change in potential. It's change in plus change in. That's the thought process. Work? Oh, force times this. It didn't work. Oh, maybe they gave me a graph. Nope. Work-Energy Theorem. And the reason I saved this one for last, it's a pain. Lots of typing and writing, and you have no idea. This will actually lead us, when we use this question to figure out how much fuel to put something in orbit, that will be the single longest question we do all year. It'll take almost an entire page. It'll be, no pun intended, a lot of work. Does this question, Kimia, if you read it, suggest any kind of hills, any kind of up and down, any kind of change in height in this question? So you know what? I think I can safely say there is no change in potential. I can modify this one. Work is just going to be, in this question, the change in kinetic. What's change in anything? This you want to commit to memory. What's change in anything, folks? Okay, so my next line, I'm going to say this. Work equals kinetic final minus kinetic initial. And kinetic energy from your formula sheet, Kimia, is what?
Sorry?
Kinetic energy, the equation from your formula sheet, is what? So kinetic final will be a half mv final squared minus a half mv initial squared. And then right around here, or maybe on the previous line, I would have asked, are any of these zeros? This is 0. So I'm going to get this. 0 minus 0.5 m 1200 32 squared. You're going to get a negative answer, which you should, because the car has to lose energy to come to a stop. And that's what this negative is telling you. How much work? You better bleed off some energy, otherwise you're in trouble. Negative. What'd you get? 600? 614, 400? I'll go 614,000. I'll go to 3 sig figs. Is that right, folks? Okay. Which force is doing this? Friction. Where does this energy end up going? Mostly heat. Heats up your brakes. One of the neat things about modern hybrids have a regenerative braking system, most of them, and instead of friction being what brings you to a stop, the actual battery is bleeding this energy off and turning it into electrical energy, and because it's bleeding the energy off, you're losing kinetic energy. You must slow down and come to a stop, but it's not actually doing it through friction between the tires and the brakes. It's really quite clever. Example 9. Justin, what's example 9 asking me to find? Work, you say. My first thought, don't write this down, would be, well, work equals force times distance. Don't write that down. I would scan the question. Do you see a force in newtons? Do you see a distance? Well, I see meters, but it used the word height. I mean, maybe this is kind of an MGH kind of dealio, except there's a 95 there. You know what? I think I'm going to do a change in potential plus change in kinetic. Justin, what's change in anything? This is going to be PE final minus PE initial plus KE final minus KE initial. There's my final minus initial plus final minus initial. There's my change in plus change in. Are any of these zero? Let's look at potential energy. Now, potential energy is based on height. Is there ever a time when this shell is zero high on the ground? I think it's starting on the ground. I think we can say that equals 0. And not only that, I think I'm going to argue, Grace, that the initial kinetic is 0. I think before we fired the cannon, I think the cannonball was at rest. A 19-kilogram artillery shell is launched from a cannon. Boom! At the top of its arc, it reaches a height of 245 meters with a horizontal speed of 95. What's the minimum amount of work? So now I think I can calculate this and understand to try and do this somehow by taking into account the parabolic trajectory and finding what angle theta, and it would be very difficult. Work as a scalar, doesn't care. Oh, I like that. It's going to be mgh final plus a half mv final squared. Mr. Dueck, does the m cancel? Is there an m in w? Is there an m hidden right here? Then m does not cancel. It's going to be 19 times 9.8 times 245 plus 0.5 times 19 times 95 squared. (19 times 9.8 times 245 plus 0.5 times 19 times 95 squared). You got 131,356.5. I'll go 131,000. Is that, yes? 3 sig figs is what I'll go to. And joules. Mr. Dueck, why did you say minimum amount of work? What am I ignoring here, which would probably actually take a lot of energy away from this system? Yeah. And I love the way you use air friction now. That would be a force over that distance. In fact, we'd be heating up the air. We'd be actually losing a lot of energy to heating up the air because the energy's got to go somewhere. Last one. I like example 10. I like example 10. I like example 10. Example 10 is a nice question. It's a nice question, Chloe, on several levels, not the least of which it seems really tough and it's going to end up being really easy, and you've had me long enough to know that I have a fondness for those. I really do. The only problem is if I gave this to you on a test, I don't like the phrasing. We're going to add one more thing. Can you write at the top next to number 10, assume the object is on level ground. So an object is being pushed on a flat surface by a force. It looks like the force is changing. The force is getting bigger and bigger and bigger. And the object is moving forward. These distances are not heights. It's moving forward. In fact, I think this object would be speeding up, speeding up, speeding up, speeding up, speeding up, speeding up, speeding up. Chloe, what's this question want me to find? How fast? Well, Chloe, what kind of a graph did they give me? And it says after 0.8 meters. So you know what I would honestly do first? I'd probably do that just so I had drawn something and wasn't panicked. Oh! What shape did I just create? Starts with letter T. Triangle, and that's going to be how much work. Why don't I figure that out? So I'm going to say this. I'm going to say work equals, write the word area in your notes so you know what the heck our thinking was. If you skipped the word area and went straight to plugging in the numbers, I wouldn't freak out on a quiz or a test. But so studying, it's a triangle, so it's going to be base times height divided by 2. Looks like the base is 0.8 long. Looks like the height is 16 long divided by 2. 64? 6.4. Yes? No? Double check me. I think 6.4. It's 8 times 8 with a decimal. Yeah? Units, joules. Of course, Chloe, that's not what they asked. What did they ask me to find? What did I just find? What's another way to write work? The Work-Energy Theorem, not force times distance. I can't use force times distance because I have a changing force. So that one, no. But what's another way to write work? And that one works, no pun intended, for pretty much anything. So now I'm going to say work is also change in potential plus change in kinetic. Chloe, what did I have you write next to the number 10 there that I should have included in the instructions? Which means no change in potential. Now, does the equation contain a V in it? I'm starting to see where I'm going, because you were right. You said this question's asking how fast, and I don't have any how fast here. Chloe, what's changing anything? So this is going to be a half m v final squared minus a half m v initial squared. Oh, Chloe, what 2 words did I just underline? Haha. And you know what I'm going to write on the left-hand side? I'm not going to write W. You know what I'm going to write instead? 6.4. Yes? What are we trying to find? Oh, let's get the V by itself. How do I move the M over? And then you can also divide by 0.5 or times by 2. I like to times by 2, so I'm going to write the next line as 2 times 6.4 divided by M. That equals V final squared. Chloe, talk me through the final step. How to get rid of a squared. Oh, look at that. So I'm going to get the final speed is going to be 2 times 6.4 divided by 25 square root. 2 times 6.4 divided by 25 is the answer. Oh, I almost forgot to square root. I was so happy because it looked like a nice answer, but no. Square root, you get 0.716 meters per second. So that's a nice little question as well. I guess the other thing I could have done is told you how fast and asked you to figure out the mass of the object. Okay, could handle that too. But nice question there. Some good thinking we can do. What's your homework? I'm going to be throwing a lot of these at you because we're starting a new unit. We need to get familiar with it. So instead of telling you which questions to do, I'm going to say cross out number 12. Really, Mr. Dueck? Number 12? And I think that's all I'm going to say. Cross out number 12. Give me 2 seconds. Right click.